So this is a question bipartite graph in which we have to return true or false on the basis of whether the graph is bipartite or not. Okay, so first of all, what's the meaning of this bipartite? So first I'm writing the general meaning of the bipartite and in which specific direction of the meaning we are using in this question, in this coding questions there. So a graph is a bipartite. It means what we can say. It means simply if we have to divide, let's say I have to write the graph here. Okay, so now what it means, graph is when we are saying it as a bipartite, so we have to divide this in our let's say we can say here. Okay, so what it means, it's nothing but the so I can say here, so it means we have to divide our nodes into two groups. And what's the condition for it? We have condition that the node of the two edges, or we can say node the two adjacent edges there, adjacent of same group. Okay, so that is the meaning of the bipartite. What it means, let's say we have to any of the graph here, let's say this is of the three nodes there, this is of the four node, so these are dividing in the two groups. And in this question how it is dividing, so this is dividing on the basis of color. So let's say these are two are the green and these two are the gray color. Okay, so what it means, if it has to be bipartite, for it which I can say no of the adjacent nodes should not sharing the same color there. Okay, so what it means, that I already written here, we can say no of the adjacent edge of the should belong to the same group. Okay, so that's the meaning of the bipartite graph. So what is the equivalent idea that I using here, like in this question, it is dependent on color dependent. So finally we can say one thing here, first of all the graph should have the two color there. Okay, and what is the meaning of the bipartite? It means let's say if I have to use any of the let's say there is a graph, there's a one node there, there's a one node there, there's a one node there, there is a one node there. Okay, and these are connected in such manner. Okay, so if these are connected in such manner, okay, so these are divided, so either they are divided in any other manner, but in the question we are using they are divided in the color way. Okay, so what it means, it means their colors, their adjacent colors should not be the same. Okay, if it is same, so it doesn't mean it is a bipartite there. Okay, so that's the meaning of the bipartite there. Now since for the how to do this question, okay, now let's say we have to see this question, there's a 0, 1, 2, so there's a no edge there which has which share the same color, so it means it is simply bipartite. Okay, coming to this question here, if we have to see this, since this is of 3 length, so here it is not possible that to make to color these nodes, because we have to use only the two colors there. Okay, if there is a multiple colors are possible to coloring them, so it may be possible or it become the bipartite. But if only the two colors are possible there, so it doesn't it is impossible to make in such a manner such that this 3 length cycle there, such that no of the two nodes share the same color. Okay, so what it means, so I can say how to do this part here. Let's say I'm using the one of the graph there, let's say this is one of my graph there, there's one node, there's a one node. Okay, these are simply connected with each other, and let's say they are just extended to it, means there is a cycle. So basically this is a whole as a graph there, and there is a contains one cycle here. Okay, now let's say I have to check whether it is bipartite or not. So let's say I'm assigning the color here, let's say this is a simply green, and after it we can say simply use blue. Okay, so I'm using the two color, green and blue. So after it we have to assign the different color, because as it should not the color of the adjacent, so that's why using the green color. Okay, and since it is a green, it means it should be the blue there, and if it is blue, so it should be the green there. Okay, but now if you have to check what's the problem here. So if I see for this edge there, its one node color is blue and other node color is blue. Okay, so if I'm if I'm draw the color of this node according to this node, so if I'm making this as a green to avoid the we can say to avoid the contradiction from this node, but in that case it has to solve the problem with this node. Okay, so it means there is an it cannot be the bipartite, means there's at least one edge there in which the two of the nodes share the same color. Okay, so that means this is a not bipartite graph. Okay, so wait, take a let's say this is our example one. Let's take another example in which, let's say, we have the one node there, and one node there. Okay, and let's say just extend it. Okay, now we have to color it, whether we can color it in such a manner no of the edge is sharing the same color node. So let's say if I have to assign in the green color here, it is a blue color here, it is a green color here, it is a blue color here, and it is a green color. So it means if I'm verify it, so it is already valid there, so it means it can be the bipartite graph. Okay, it can be the bipartite, so it means it is giving the true there. Now coming to the next, let's say there is a one node there, there is a one node, there is a one node there, and there is a one node there, and there, let's say there is a, okay, so let's say they are connected in such a manner such that, okay, so if I'm assigning color it is, if it is a blue, then it should be the B, then it should be the green, then it should be the wait a second, it should be the blue there, then it should be the green, then it should be the blue. Okay, if I'm checking all over the array there, so there's all are the color are assigning in the true manner, means it can be the bipartite because it doesn't contradict with any of the edge there. So like what we can extract from it, we can say one thing, like a graph can be bipartite in which case is there, like if I'm to write there. Okay, so if our graph is simply the linear case, okay, so in that case we can simply say it can be the bipartite there. Okay, and let's say if there is a cycle contains, but if its length is simply the even, there's a even length there, so it can be also bipartite there. Okay, so these are the cases when it is bipartite. When if I'm talking about the in what cases it can be not bipartite there, so like only the case remaining here it is when we have the cycle with, we can say, our odd length is given there. Okay, let's say what we discuss here, so there's a 3 length out there, so there's a cycle it contains, so in that case it does not possible to make this graph as a bipartite, so it means this is the only case in which it is not a bipartite. Okay, so now simply we have the two methods we can do by either using the BFS or DFS. So in this video I have to do using the both of the methods here. So simply if I'm going for the BFS, so how to do this? First of all, what we need, we simply use our color array there. We have to maintain our color array to storing all of the colors of all nodes there, and like let's say we have to initialize our with -1 there, so that it means it is simply not colored there. Okay, so it means it is not colored there. And what is after it we can assigning the two colors. Let's say we can assign our 0 and 1 there. Okay, we can assigning any of the color there. Okay, so 0 and 1 means 0 is one of the color, 1 is the other of the color there. Okay, so means two different colors configurations there. Now what we can say, we have to check for we can say for unvisited nodes. We have to simply traverse for all of the nodes, and we have given the total value v is nothing but the total number of nodes there. So we have to see for each of the unvisited node if we have to start our BFS there. Okay, so there's no problem in it. We have to start our BFS, we have to simply assigning of the 0 color to the starting of there, and like we have to go for its neighboring and check for each of the neighbor. If now what's the thing here, we can say for its neighboring, like what are the scenario come here and around there. So if it is let's say we are arriving at this position, so what are its neighbor? It is there's a green, and since we are come from it, so it is already colored. Now when we are arriving to a such neighbor such that it is not colored, so in that case we have to simply, we can say, if it is not colored there, so in that case we can simply assign a opposite color there. Okay, so we can simply assign the opposite color there, and just wait a second there. And like what is the Coming to the another thing, in that case if it is colored, so now again the two things here. Let's say we are arriving at our neighbor and it is already colored, so we can say if it is already colored there, okay, and it has the same as color as our current color, so in that case we can simply return that it is not bipartite, okay. And if it is not colored there and it is assigning the same color, so a different color, we simply skip that part, okay. So these are the like possible configurations possible in it, okay. So now simply coding this part here. So this is our BFS code there. There is a main function. Simply first we maintain our the color vector there, traverse our all of the nodes there. If color is -1 means it is non-visited there. In that case we simply have to do the BFS for this. Why we do this I0 to V? Why we don't use to simply call for the BFS of starting node? Because there can be the distinct, or we can say there can be the multiple components. So to cover all of the component there, that's why I have to traverse for all of the nodes there, okay. So simply we have to check for the BFS for this. So what's the definition, or and in which if any of the case arise in which the BFS returns false means it is not possible, so simply return false, and after covering or we have to simply return the true value here. There's the definition of BFS. Like what are the things I pass in this? There's a first of all in starting node there, there's a adjacency list there, there's a color vector there. So simply traditional method of the BFS using the queue, simply put the starting node in our queue, so and assigning its color as, simply initially we can assign the color as 0 or 1, it doesn't matter there, okay. Let's say assigning the color there. Now since after covering this, we know very well like all of the nodes are automatically coming together and push in the our queue. So what are the our main agenda there? We simply have to, while a queue.empty, we simply have to run this code until our queue is become the empty then. So first of all extract our front node there, simply pop element from that queue, okay. Now we have to see for the neighbor of that node there, okay. So now there's a condition, if that neighbors is unvisited, this color is -1 is denoting means it is unvisited there. So in that case we have to simply assign the color as opposite color, means if it is 0 initially, so it become the 1 - 0. If it is 1, so it become 1 - 1 means 0, okay. So simply the opposite. So that's why to handle these cases smoothly, we simply has to take the color 0 and 1. We can also take color as red, green or blue, green. So there's nothing called the change for this, okay. So simply assigning the color and simply push that neighboring node in our the queue there. And this is the case when we have to find our unvisited. Other remaining cases when we find the visited case, in which case there is one crucial case when we have to find one visited node and its color is already same that our current node. So what it means? Simply return false there. And after covering all of the when this queue become the empty, simply return the true, means we are not find any of the contradiction to or any kind of the conflict regarding the bipartite condition of this graph. So simply return the true in this case, okay. Now coming to the time complexity, we know very well like this is the simple BFS code there. So what's the time complexity for it? This is nothing but the simply we can say of V plus E. And what's the, like if I'm writing the time complexity for it, it is nothing but the V of V. And if I'm talking about the space complexity, it is nothing but the of V there, okay, because of this color vector initialization, okay. Coming to the DFS part again, so if I have to go for the DFS part there, so like again the all of the things remaining the same. We know very well that our the definition of our bipartite is here, that node to adjust, like I can write here, okay. Let's again write here, we can say if our node to adjacent have same color, okay, because we have to see here in term of color there. So that's why I have to use this. So that's the meaning of our bipartite here. This is nothing but the bipartite, okay. So while doing DFS, we have to like if I have to now this time we have to follow the configuration of DFS, so simply we have to simply we have to doing our DFS from the starting node. Try assigning the whatever the alternate colors there, and if any of the conflict arises, we simply return that it is not a bipartite, means there's a graph is not bipartite graph. Okay, so what's the approach for the DFS? Along again the same, simply maintain our that color vector there. -1 means it is not colored, or we can say not visited there, and if we can say here, okay, not visited there. Okay, and for the two colors are possible, 0 and 1 there. For each of the unvisited node, we have to start our DFS. Okay, we can say we have to start our DFS with the color 0 there, and in the DFS again we have to see for the neighbor, if it is not colored, assigning a different color. If it is already colored, means already visited and has the same color, simply it means it is not bipartite. Coming to the code for the DFS, so there's the main function, there's again the same thing. You have to check for the DFS for any of this. So there's the definition. See here, like here I have to pass the one extra parameter here, because when I'm calling for the DFS was 0, so when it is going in its neighbor, so it also need to know like what is the color of this current node, that should be reminded for moving into the neighbor color. So that's why it has also stored the color for its current node there. So that's why there's a current node, there's the current color there. So that's why into node there, it call means simply the color, adjacency list or color there. Simply initially color this node there, so color node is become the call, and after it we can say for int I is equal to adjacent of let's say what is okay. So there's nothing but the there's a for int of it, so going to its neighboring part, see if it is not visited. Now since if it not visited, we have to check by chance any of the by chance we have to see if in its neighbor returning any of the false there. So if its neighbor returning the false, simply return false there. Okay, and if it doesn't return the false, we simply have to move to this direction there. Okay, other condition, if let's say it is so there's a condition covering in which it is not visited. Now other thing, when it is visited, and if its color is already the same as of our current color, means simply return the false, and after returning all of the traversing all of the neighboring, simply return the true there. Again towards the time complexity and space complexity remaining the same, because we know the DFS and BFS time complexity for this is same there for this standard questions of the actually this BFS you know very well, like this is there's nothing but the recursion plus we can use our color array. Okay, similarly things goes for this. Okay, like there's a DFS also calling there, so that's why it takes a recursion space there. So that's the thing there.